Okay, welcome back. Happy Friday. Today we are talking about comparison tests and the ratio test. We have no classes this coming Monday because of Patriots Day. Evening classes meet as scheduled. So if you have a Monday night class, go to that one. But no day classes, so we don't meet again until Wednesday coming up. On Wednesday coming up, project number 7 is due, so hopefully we're making good progress on that one. We've got another day of new stuff on Wednesday coming up, but then 1 week from today, we have our one and only catch-up day for this semester, just a chance to kind of catch our breath. I don't have any agenda on that day. We're just going to come in and practice on all of these tests that we've been learning, just a day to catch our breath. Any questions on the calendar? Okay. So looking at the top here, in this class, we learn how to use the comparison tests and the ratio tests to determine whether a series converges or diverges. With apologies, today's lesson involves a long demo and a short activity. It's the best lesson plan that Caitlin and I have come up with, and it is what it is. There's just a lot of stuff going on in today's material. Let's begin by reviewing the convergence tests that we've already studied. By looking at the reference sheet on tests for convergence, it says separate handout. It's not. It's page 1. So just go right now to page 1 in your packet, which I think looks like this. Yes? Okay, so this is a summary of all of the different series tests that you are going to be responsible for by the end of this semester. It says the series tests on this sheet apply to the generic series sum of a sub n. N equals 1 to infinity is the norm, but anyway, that's implied here. And so I'm just going to run through the list, this first column here, the name of the test. We've talked about geometric series. In the activity, which not everybody got to, but I'm hoping we got to outside of class, the p-series test. Did we have a chance to look for p-series? We talked about the nth term test for divergence, and we talked about the integral test. So I think we have done the first 4 of the things on this sheet. Today, we're going to tackle the next 3. Comparison test, limit comparison test, and ratio test. And then 2 more Wednesday next week, and then that'll be the end of the list of tests. So coming up here, let's, for example, take a look at the integral test, just so that we have a sense of how to read this complicated looking sheet. Okay, the integral test. It says you use it for a series which is a sub n equals f of n, where f is positive and decreasing from some point onwards. So remember, for the integral test, the first thing we did was change the terms in the series to just a function. Oftentimes we just say f of x. And you needed that function to be positive and decreasing. And then the conclusion in the next column, it says that the series converges if the integral converges. And in the next column, the series diverges if the integral diverges, right? And so we do a lot of work to try to figure out whether that improper integral converges or diverges. And then the integral test says that the series does exactly the same thing. Last column, the test tells you nothing if the integral can't be evaluated, right? So you can't just apply the integral test to every single problem because it relies on being able to do an antiderivative. Okay, and so the other 3 rows we've tackled, but anyway, it's all here in kind of a nice format. We are going to spend some time, not today, talking about the next page, which says testing series for convergence will always involve some trial and error. I've tried to indicate some things to look for that might save you time, and this is the process, the order in which I run through the various tests. We'll talk about that order in a coming class, like when we've got more of these tests under our belt. Okay, so let's come back to, I think it was 28. All right, number 2, the first test for convergence for today is the comparison test, or the direct comparison test. This test is very similar to the comparison test for integrals that we studied earlier in the term. Let's give it a shot here. We're going to try to figure out if this first sum converges or diverges. Sum of 1 over 3 to the n plus n. 1 over 3 to the n plus n. So just running through the routine, we currently have 4 different series tests that we know about. First thing that I always ask is what happens to the terms when n goes to infinity? So if n gets really big, then this bottom gets really big. And so what about the whole fraction? Goes to 0. Is that good news for us or bad news for us? It's bad news, because 0 tells us nothing. If it had gone to 2/3 or -1/5 or anything other than 0, then what can you say about the series? then it diverges, right? That was our test. If the terms do not go to 0, the series has no hope of converging. So it's worth a shot. It didn't work. Next thing up, is this a geometric series? Well, you can plug in a few numbers if you want to, but you'll see that it is not a geometric series. Like if you list the first 3 terms, you'll see it is not the same multiplier over and over again. P series, that's kind of an important one for us. We'll just remind us over here, 1 over n to the p. That is the definition of a P series. And they're really easy as long as you know the P series result. Is that thing 1 over n to the p? It's not. And then the only other test we had was the integral test. So we ask ourselves, what do we think about doing this integral? All I've done is change the n's to x's. I don't know what you think, but I think help. I don't know how to do that integral. So we had 4 tools, none of them is going to work. So we need a new tool, and that new tool is going to be this brand new thing called the comparison test. So here it goes. 1 over 3 to the n plus n has 2 pieces in the bottom, the 3 to the n and the n. So I'm going to compare that fraction to one of the pieces. And I'm also going to compare the original fraction to the other piece. So we're going to put an inequality inside, either a greater than or a less than. So if I ignore numerators here, what symbol would go in between these two? Greater than, right? Because everything's positive and an n are the same, and we've added 3 to the n. So we would put a greater than symbol in there, but then we do fractions, so what symbol goes in between? Less than. Everyone agrees? First fraction is less than 1 over n. How about in the second case? Here, we ignored the n. We're comparing just to 3 to the n. What symbol goes between? Also less. It's for the same reason, right? Okay. So I know that the terms that I'm interested in are less than the terms in 1 over n, and they're less than the terms in 1 over 3 to the n. I don't know if one of these is going to help me, if they're both going to help me. I'm just not sure yet, but I've got the only 2 natural inequalities I can come up with at the moment. So let's consider this series here, sum of 1 over n, and then separately, sum of 1 over 3 to the n. The hope is that we can get information about our series by getting information about the easier series that I just wrote up there in red. Sum of 1 over n. That guy has a name. That is the harmonic series. It is always the harmonic series, 1 over n. Does it converge or diverge? It diverges. It's a fact. You saw it last time. It actually is an example of a P series. How much is P? P is 1. 1 is the cutoff between the convergent and divergent P series. This is the divergent harmonic series. No, so it might kind of look funny the way that I've written it there. I am telling you that it diverges, and the rationale, the reason that I can tell you it diverges is because I am sharing with you that I know it's the harmonic series, and it is just known that the harmonic series diverges. Yeah. Okay, so the question is, does this blue inequality, that first one, help us? The terms that we have are smaller than the terms in a divergent series. Can we make any conclusion about our series? No. Our series is smaller than something infinite. Don't know. If it's not that much smaller, it's probably still infinite. But if it's a lot smaller, then it's going to be finite, right? So it's just not helpful. But I didn't know that ahead of time. So let's try the other one. 1 over 3 to the n. Writing out a few terms of this guy. When n is 1, when n is 2, when n is 3. What kind of a series is that? That is geometric, right? Same multiplier every time. This is a geometric series with, what's the common multiplier, common ratio? What is it, 1/3? What's the interval for geometric series to converge? -1 to 1. Since X is definitely between -1 and 1. What do we say about our about this particular geometric series? What does it do? Yeah, it converges. So 1 over 3 to the n converges. Notice here that I took the extra 2 seconds to write summation of 1 over 3 to the n. I didn't say it converges. I didn't say the series converges. You shouldn't do that either. When you say the series converges, look, 1 over 3 to the n, that's one of the series on my page. 1 over n is another series on my page. Turned out not to be helpful, so maybe you don't even have that on your page. But the series that I care about is definitely on the page. So you cannot say it converges. You cannot say the series converges. Well, you can, but then you're asking me to figure out what you mean. And I've got a red pen in my hand, and I'm quite happy to use it when I don't know what you mean. Right? So take the 2 seconds to actually write the sigma. Okay, so then I think we're good to go here. The terms, right over here, the terms in our series are all less than the terms in the 1 over 3 to the n, and that was a convergent geometric series. So if the sum of 1 over 3 to the n is finite, what about our sum? It's got to be finite, and it's smaller, right? So we just have to write a little sentence here. Okay, since this is us just kind of summarizing, I'm going to copy that second blue inequality. 1 over 3 to the n plus n is definitely less than 1 over 3 to the n. And since the sum of 1 over 3 to the n converges, we've already demonstrated that. What do we conclude about the original series? What does it do? Also converges. Sum 1 over 3 to the n plus n also converges by the CT comparison test. So named because we did a comparison, right? That's what the inequality was. We compared our terms to the terms in a series that was easier, that we knew about. That's it. And so, like the comparison test isn't formally written up on this page like the theorem itself, but it's something that I think is sort of intuitive. If your terms are less than something convergent, then your series converges. On the flip side, if your terms are greater than the terms in a divergent series, then your series also diverges, right? So just have to have the inequality going in the obvious direction, the natural direction. Okay, let's take a look at the next one. Same idea, but 2 fractions here. 1 over 3 to the n plus 1 over n. Okay, so 1 over 3 to the n plus 1 over n. I suppose I'm doing the same kind of comparison here, right? I'm going to put an inequality there, and I'm going to put an inequality here. What inequality goes in between in the first case? This left-hand one is greater, right? Because you're adding something positive. 1 over n, but we're adding something positive. And how about over here? Also greater. 1 over 3 to the n, but just add a little bit of positive stuff, and it becomes greater. Pausing for 1 second. I know that sometimes I am wishy-washy and I say, oh, n is really huge, so you can ignore this and we can ignore that, and the only thing that's important is a leading term or whatever. But this is not wishy-washy. This is us really solidifying. I'm not saying ignore the piece that we don't want. I'm writing down true inequalities. And now we're going to use this comparison test. Okay, in your minds, think about this one over here. Summation of 1 over 3 to the n. Converges or diverges? That converges. We saw that one. So that means that our terms are greater than the terms in a finite, a convergent series. Helpful or not helpful? Not helpful. Our stuff being bigger than something finite, I can't make any conclusions. What about this series? Diverges. Our terms are bigger than the ones in a divergent series. Helpful or not helpful? Our terms are bigger than something infinite. That's great. That means that our thing is also infinite. And so we just have to write it up. Okay, so since 1 over 3 to the n plus 1 over n is greater than 1 over n, and since summation 1 over n diverges, and I know that I said that that guy diverged earlier because we just know the harmonic series diverges. I'll write this one in a different way just to give us practice in this different way. I said that is a p series. How much is p? So if we just write p series, it's p equal to 1. And we said the cutoff for the convergent divergent for p series is what number? It is 1. And which is the divergent side? Greater than 1 or less than 1? Yeah, it's the less than side is the divergent side. So we just, if you put that, that is making it very clear to the reader, you know exactly what's going on with this p-series test. Right, so that thing in the parentheses justifies writing the word diverges. Okay, so since our terms are greater than the terms in a divergent series, then, let's see, so since this and this, then we know that the original series, and I'm writing it out, 1 over 3 to the n plus 1 over n, what must it do? It must also diverge by the comparison test. Yeah, you can see I was like super sloppy, right? I didn't write them a single time. No, not really. The only important thing in terms of these limits here is that it's infinity. And it could start at 1 or it could start at 1,000,000,000,000, right? It's always the infinity part is the thing that makes or breaks it. Yeah, so I'm being sloppy. It's okay with me if you don't even bother writing those limits in. Okay, so that is the comparison test or the direct comparison test. We saw both cases. First one, you showed that your terms were smaller than the terms in a convergent series. That was helpful. Second one, we showed our terms were bigger than the terms in a divergent series. Notice that I wrote both inequalities. I didn't know which one was going to help me ahead of time. So you just write, like, really, I made a false start here, and it kind of looks smooth the way that I presented it, but one of these was a false start, and that's how it goes. You're not supposed to know ahead of time whether or not the inequality is going to go in the right direction. You're just figuring out the inequality, and you're hoping that it's something useful. It isn't always. Okay, next page right here. Says, let's use the comparison test on this series, n over 2n squared plus n plus 1. N over 2n squared plus n plus 1. Okay, so if I wanted to compare this to something, let's see here. I'm not even sure I believe what's written here. If I wanted to compare, forget about this guy for just a second, but 2n squared plus n plus 1. Well, maybe I do believe it. Okay, if we were to, remember I said we could be wishy-washy sometimes. What can I ignore in the bottom if I'm being wishy-washy? The plus n plus 1, right? It's only about the leading term. Okay, and if I reduce in that fraction, what do I get? 1 over 2n. So it feels to me like 1 over n is the thing. Like this is ultimately like 1 over n where I ignore some stuff. But you can't just ignore it. You got to solidify it with some theory, which is what we're interested in. So we'd really like to compare this thing to this thing. And so like if I wrote, you don't need to write this. But if I write this and with a blank inequality symbol in there, it should not be obvious what inequality to put in. Because the tops are not the same. And even if I made them the same, the plus n plus 1 and then the times 2, I guess they're all kind of working together. It feels to me like it goes that way. Like that denominator is definitely bigger than this one. So I guess technically we can use the comparison test. So let me ask you this. If you believe, and this is a tougher inequality maybe than the ones that we've written, but if you believe this inequality to be true, and what did we say about the sum of 1 over n? It diverges. So can we make any conclusion about this sum? No. But my goodness, if that thing behaves like 1 over n, then the fact that it's like a tiny bit smaller, it doesn't seem like it should make much difference. And I say a tiny bit smaller, I mean, it's like half, right? It's like half as small. But half of infinity is still plenty big. It's still infinity. And so the direct comparison test does not work here. That doesn't mean that the series converges. It doesn't mean that. It doesn't mean the series behaves differently than 1 over n. It just means that we cannot attack our series directly because the inequality doesn't go in a helpful direction. And so in lieu of the comparison test, the direct comparison test, we're going to do something called the limit comparison test. So here it goes, brand new test. You're going to copy your term. So go ahead and write this in here. And you are going to divide it by the term in the series that you think yours behaves like. And we were thinking, maybe, just maybe, our series behaves like 1 over n. So we're going to put that 1 over n right there. And so there was a lot of work that we did in getting to the place that we could figure out the 1 over n. And what I'm going to put in the front of this thing is a limit as n goes to infinity. Yes. Yeah, and that's a really good observation there, is that there are plenty of things we can compare the series to, but all of our comparison tests say that your series and the series you pull out of a hat behave the same, which means that it's only going to be helpful to us if the series we pull out of a hat is one that we know whether it converges or diverges, right? So you don't want to just make up any old series, because if I say this series and this series behave the same, but I don't know what either of them does, that doesn't help me, right? And so I'm giving you a series you don't know about. You better compare it to a series that you do know about, and then you can say, hey, since they behave the same, then the series I want must do this thing. Yeah, so we're picking something intentionally that we know whether it converges or diverges. Okay, it's not clear to at this moment like what we're doing with this limit, but let's just do this calculation here. Limit n goes to infinity. What's our standard technique for fraction in fraction? It's multiply by reciprocal, right? So copy all this stuff here times n over 1, right? Okay, I'm going to write the one single answer right now. I want us to know what this limit is just by looking at it. Upstairs is an n squared. Downstairs, you really can ignore everything except the leading term. So what does this thing approach? Half. Everybody agree? This thing approaches 1/2. Okay, so what are we supposed to do with that? The answer here is 1/2, and the answer to like a made-up limit that I pulled out of a hat myself. All right, so check this out. Here's the formal statement of this brand new thing called the limit comparison test. It has 2 series involved. The 2 series that we have are the one that we started with, circled here in blue, and that sum of 1 over n circled over there in blue. Those are our 2 series, A sub n and B sub n, okay? So it says, we got to make sure that everything is positive at some point. All that stuff up there is positive with n equal to 1 or greater. And then it says you divide, and you take a limit, which is exactly what we did right there. A sub n over B sub n. It says if this limit is finite and not 0. Finite and not 0. What was our limit? What did we get for our limit? 1/2. Is it finite and not 0? Yes, it is. And the conclusion of this limit comparison test is that the sum of the A's and the sum of the B's both behave the same. They either both converge or they both diverge. They behave the same. So we'll talk about this really funny highlighted yellow thing in just a second, but let's apply this theorem to our example right now. Nick?
I'm still just not totally. Even if it's 1/2, plus n plus 1, you know, say you're up at, a billion,
yeah.
You still have a plus a billion and 1.
You do. But with that plus a billion and 1 in the bottom, maybe it's 0.499997 or something like that. And if we go out to a trillion, it's going to be 0.49 and then even more nines. But honing in on a half, never actually getting to a half, but that's okay. It approaches 1/2 and it gets closer to 1/2 than anything you can name. Is that let's do a calculation here. So it's n squared on top, right? And 2n squared plus n on the bottom. So x squared on top, and then 2x squared plus x plus 1. Do I have that right? Nope. How about that? Nope. How about that? Good. Okay, so this thing. And if we plug in, so I'll plug in something smaller initially. So when I plug in 10, and when I plug in 100, and when I plug in 1,000, and so yeah, the plus n plus 1 makes it so it's never exactly a half, but it is sure compelling that it looks like it's going to a half. Okay, so really strange thing here in yellow. We'll talk about it, but let's make our conclusion up here. Since, something I forgot to do. I like to call my limit here L. So if you could squeeze like an L equals in there, just so we don't have to write that whole limit calculation again. Since L equals 1/2 is finite and not 0, the two series behave the same. And I know that I kind of just broke my cardinal rule about writing the series, but honestly, there's exactly 2 series on this page, circled in blue. I don't think there's any confusion about what the 2 series are. What do we know about the second series, sum of 1 over n? That diverges, it's harmonic. The limit comparison test says the 2 series behave the same, so what about our series? Also diverges. So, since sum of 1 over n diverges, again, it's the harmonic series, then the sum, and then I'm copying the whole original thing, also diverges by the LCT, limit comparison test. They make they approach a finite number, right? But what that means is that the terms in the 2 divergent things, even though the sums are both approaching infinity, the terms are roughly 1/2 of each other. And so half of infinity is still infinity, but they're both kind of going to the same infinity, just one at exactly half the rate of the other.
You're not comparing the sums, really, you're comparing.
I'm comparing the individual terms, not the sums. Yeah. Okay, so let's talk about this whole finite and not 0 business. One of the strangest conditions you'll ever see in a theorem. I mean, like again, a geometric series, what's the convergent interval? -1 to 1. Okay, that's, it's like a length of 2, right? What's the interval that we care about here? Finite and not 0. Infinity. Anything between 0 and infinity and you win, right? Anything between 0 and infinity, you win. Okay, so let's take a look at these two series right here. 1 over 5n, brand new, not related to the ones up above. 1 over n, what's that? So the no, because we're only applying this to things that are positive in the start. Okay, 1 over 5n and 1 over n squared. Do you believe that these two series behave the same? Is this a good comparison? What does 1 over 5n do? That diverges. That's the harmonic with the 5, right? How about 1 over n squared? That converges. That's a p series. P equals 2. It's bigger than 1. So these two behave differently, right? And if you didn't know anything about 1 over n squared, and you said, hey, I'm just going to compare 1 over n squared to 1 over 5n because I know 1 over 5n diverges, you are wasting your time, right? Like this is a bad choice to compare 1 over n squared to. And the other way is a bad choice as well. But let's suppose that we just made that bad choice. So check this out. If I do 1 over 5n divided by 1 over n squared, go ahead and write that, right? Where we divide the two terms and we're hoping for something finite and not zero. If we can get finite and not zero, then they behave the same. And there's a limit as n goes to infinity. And we do our standard flipping thing. 1 over 5n, n squared over 1. So once you've copied, take a moment to write down what that limit is equal to. Okay, n squared on top, 5n on the bottom. What's the limit? Infinity. That means that the one fraction on the top is like infinitely times as big as the fraction on the bottom. It means there is no reason to compare these two things. I'm not saying they do something different. Like just because you get infinity doesn't mean one converges and one diverges. It means that there's no reason for you to compare these two things. There's no reason to think that they behave the same as each other because they're related, you know, like in some way. What if I had flipped this thing over? Which one you call A sub n and which one you call B sub n makes no difference. So you're always welcome to flip the thing over. If we had flipped over in here, what would we have gotten as the final limit? 2. Is it finite and non-zero? Yes, no problem. Okay, so don't worry about which one goes on top. But over here, if we had flipped this thing over, yeah, so 1 over n squared, 1 over 5n equals dot 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 equals 0, right? It'd be a 5n over n squared. So that's why 0 and infinity are somehow like the same, right? It's because it's just which way do you divide? Okay, so let's take a look at this next one, number 6 here. It says, what's the problem with using the comparison test for this series here? N squared over 2 to the n. N squared over 2 to the n. So first I will say that is not geometric. It is not a p-series. I don't know how to integrate that thing. And the direct comparison test isn't going to help us either. Let's try the limit comparison test. We're just going to do highlights because it is also not going to work. If I wanted to compare to something that I know about, right? Levi says, you better pick something you know about. Okay, I know 1 over 2 to the n. That's a geometric series. And I know something about just n squared, like ignoring the top or ignoring the bottom. N squared, that's a ridiculous thing to add up because the terms go to infinity. So definitely that one diverges. So if I could somehow use this limit comparison test to compare to either of these, I would win because I know what each of these does. One converges and one diverges. Again, just the highlights here because it's not going anywhere. N squared over 2 to the n divided by 1 over 2 to the n. Comparing to the first fraction. I'm just going to save a little bit of time here and do our automatic flipping thing here. And this guy is equal to n squared. I haven't been writing limit, but as n goes to infinity, what does this one go to? Infinity. Is that good or bad for using the limit comparison test? It's bad. We were looking for any number between 0 and infinity. We could not find something inside of that range. If we instead compared the original to the other guy, say in this order, again, I'll be a little bit lazy here, do our automatic flipping thing. What is this equal to when I reduce? 1 over 2 to the n. And as n goes to infinity, 0. Means that we cannot use the limit comparison test on either of those two things in blue. Just didn't work. Okay, so we need a new tool. Next page. Enter the ratio test. So we've seen 2 tests today. This is our 3rd and final test for the day. It's the ratio test. Here's what it says. This whole thing, this whole theorem is the ratio test. So it says you have a series a sub n. You take the limit of the absolute value of a sub n plus 1 over a sub n. What that means is that you are looking at, you're putting the general term in the bottom of a fraction, and you're putting the very next term in the top of a fraction, okay? Notice there's no b sub n's. We're not comparing to a second series that we pull out of a hat. This is just a single series. And we do this limit as n goes to infinity of that ratio, and we're going to call the answer L. And based on what we get for L, we're going to make conclusions about the original series, whether it converges or diverges. It says if L is less than 1, then the series converges, and that's it. If L is greater than 1, the series diverges, and that's it. So the magic is just finding that L. If you can find the L, the limit, anything less than 1 or greater than 1, and you got your conclusion. Sadly, if L equals 1, the test is inconclusive. You got to try something else, okay? But anything other than 1, and we have a conclusion. So let's give this a shot, and then I will explain why you should believe any of this stuff that's here. Let's try number 8. So here's the series that we just talked about. And let's do our calculation. Limit n goes to infinity, absolute value, big fraction line. So in the bottom, you put the current general term, which is given, n squared over 2 to the n. Upstairs, you put the next term in the series. That means all the n's become n plus 1s. So up here, what do we get on top? N plus 1 squared, right? All the n's become n plus 1s. Downstairs, 2 to the n plus 1. Everybody see that? Okay, so before we finish our limit calculation here, let me say it is crucial that you put that fraction in the right order. The bottom is always the current term. The top is always the next term. I talked about how in the limit comparison test, doesn't matter what order you divide in, a sub n or b sub n, which one's on top makes no difference. Here, it makes all the difference. It is always next one over current one. Equals, limit n goes to infinity. Okay, I'm going to drop the absolute value because everything in here is positive already. I'm going to do my standard flipping thing, n plus 1 squared over 2 to the n plus 1 times 2 to the n over n squared. All right, we've got lots of 2's floating around. Most of them cancel. What's left on top and what's left on the bottom? In terms of the 2's. Upstairs, everything cancels. Downstairs, there's a single 2 left. We've seen this before, right? There's one more 2 left over. Okay, equals. I am ready for us to write down our final limit. Maybe one little thing. This guy right here, if I were to distribute it out, it is n squared plus stuff we don't care about, lower order terms. So on the top, at its heart is just n squared. On the bottom is 2n squared. What is this limit? 1/2, right? That 2 makes a difference. Okay, we calculated the limit. That's the hard part. Now we just have to read the theorem, make the right conclusion based on the answer. This is L. L is 1/2 here. Anything less than 1, that series converges. 1/2 is less than 1, our series converges. It's a simple sentence. Here we go. Since L equals 1/2 is less than 1, the series, and I'm writing the, copying the series as it is, n squared over 2 to the n. What does it do? Converges by the ratio test RT. Converges by the ratio test. So technically, we never ignore terms, right? So I do not want us to think that I don't want us to think that's a thing. We have never ignored terms. What we have done repeatedly is okay. So going back for a second here, what we did here was say it feels to me like the plus n and the plus 1 are going to make hardly any difference. Let me compare that thing to 1 over n, which is like the simplified version of this. But it is formally written up here with the limit comparison test. So the limit comparison test is the way that you tie in, the fact that you think some terms don't matter, but you don't get to just say, oh, they don't matter, and it is the same as 1 over n. You don't get to just say that. You're comparing it to 1, which is simpler, and it turns out by the limit comparison test, that is a valid comparison to make. Finite and not 0, turns out that's totally reasonable to ignore those things, but the limit comparison test shores that up. Over here on this page, the one place where we really do kind of wave our hands is back in the Precalc theorem about horizontal asymptotes. And you guys remember if the degree on the top is equal to the degree on the bottom, then you just look at the leading coefficients. And that's exactly what we're doing here. N squared on the bottom, n squared on the top. Degree is the same. All we care about is leading coefficients. So you saw it with x's, like exactly 7x to the third plus 4x plus 1. I said find the horizontal asymptote, you'd say, oh, it's easy. The powers on the top and bottom are the same, so it's just 3/7. That's exactly what we're doing here, right? When we send n to infinity, it's sending x to infinity. It's the horizontal asymptote. I would say that's the only time where we've been wishy-washy. Okay, so let's talk about the magic that is this ratio test right here. If the limit is less than 1, it converges. If the limit is greater than 1, it diverges. What is going on there? Okay, take a look at this. We got a half here, right? What that meant was that when you take the next term over the previous term, you get a half. Another way of saying that is that the next term is roughly half of the current term. Yes, that's what that ratio is. The next term is basically half of the current term. And if that's not like crystal clear, we can do a very quickie example here. Let's pick like n equals, I don't know, 20. I'm just gonna do n equals 20 on this guy. So that might be too much. Let's see. 20 squared divided by what? 2 to the 20. Okay, so we get 0.00038, something like that. And then I'm going to do the next term, the 21st term. 20th term down here, 21st term there. So what am I doing upstairs? We go 21 squared divided by 2 to the 21st. That. And this term is definitely smaller than that term. It's not half, right? I mean, if it were half, it would have been like 1.9. So it's more than half. But the farther out that I go, so let's do like 100. I don't know if the calculator is going to yell at me. It might. Like at some point, 2 to the power becomes too big for the calculator. So if I did like 100 squared divided by 2 to the 100th. Oopsies, 2 to the 100. And then I'm just going to right now insert right in here. Put the 101st term on top. So 101 squared divided by what? Divided by 2 to the 101. I don't know if this is going to work, how close it's going to be, But what am I hoping to get roughly when I divide next one over current one? Hoping it's going to be close to but not equal to 1/2. So in this case, the next term was about 51% of the current term. But the farther out you go, this is only 100 terms. We're trying to get to infinity, so we should have gone a million, trillion, billion, all that stuff. Basically, it's basically to get the next term, you multiply by 1/2. What is it called if it actually does work out as nicely as that? Not this series, but like another series. What is it called where to get the next term, you multiply by 1/2? Isn't that a definition of a geometric series? So what this is saying back here is that we got a 1/2. This series is basically a geometric series. It's not perfect. It was 51% instead of 50%, but it gets closer and closer to a 1/2. And ultimately, this is a geometric series almost. Again, what's the magic window for convergence for geometric? -1 to 1. So everything in this case is positive because we did absolute value. So if everything is positive, then that -1 to 1 becomes what? 0 to 1, right? If the ratio is between 0 and 1, we converge from geometric series. If the ratio is between 0 and 1, less than 1, you converge. It's the geometric series test again. If you are bigger than 1 from geometric land, you diverge. And if you are bigger than 1 here in ratio land, you diverge. So this is just the geometric series test, almost. Yeah. Speechless. Speechless. All right, let's take a look at B. Sum of 4 to the n over n factorial. So this will be the first one with factorials in it for us. Can we just take a step back for 1 second? The first thing that we should always be doing is using that nth term test, meaning do the terms go to 0? 4 to the n is an exponential growth thing, right? 4 times 4 times 4 times 4, that grows super quickly. And back in pre-calculus, you were taught that exponential functions beat everything, right? They dominate everything. How about n factorial? Because if 4 to the n really dominates, and that fraction is getting bigger and bigger and bigger, then the series clearly is going to diverge, right? So the question is, how does like 4 to the 10th compare to 10 factorial? 4 to the 100th compared to 100 factorial? That's the question. Which one? They're both going to infinity. Which one's going there faster? Think about 4 to the 10 compared to 10 factorial. So that's 4, 4, 4, 4, right? 10 of them. And this is really 10, 9, 8, down to 3, 2, and 1. At the end, 4s are winning, right? And they both have exactly 10 factors. Do you see that the factorial is, even though it was losing a little bit in the beginning, it's winning here at the end and pretty easily. And I stopped at 10, go to 100, and it's not even going to be close. Yes? And okay, so you might say, well, 4 was a small number, right? So, you know, maybe this is like 53, right? If it's 53, then these are a bunch of 53s here. So which one wins if you put 10 of them? 53 wins, right? If you put 10 of them. But if you put 100 of them, it's kind of close, actually. I'm not even sure at 100. 100 is like, it's like a tie-ish. But if you do 200 or a million or a trillion, clearly those 53s are going to be peanuts compared to the numbers that we're multiplying from the factorial. So when we said in Precalc that factorial beats all, that was a lie. Factorial just got destroyed. Sorry, when we said exponential beats all, that was a lie. In fact, the factorial destroys the exponential, right? It's not even close. And you could think, well, hey, 53 to the x, that's huge. No, it's all relative. So this factorial is massive, dominates the 4 to the n, which means that fraction is going to what? 0, and it's going to 0 pretty darn fast if we believe that n factorial really dwarfs. So what is your instinct for what about the series? If we add them up forever, the terms are going to 0 really fast. Series, converge or diverge? Is definitely going to converge, right? Like these things are going to 0 so fast, but the ratio test will firm that up for us. So let's do it. Okay, so the ratio test says let L equal limit n goes to infinity, big absolute value, big fraction. Super important that you put the right thing in the right spot. Where does that original term, the 4 to the n over n factorial, go? Goes in the bottom. If you put it in the top, you will get completely backwards the conclusions for the ratio test. If you flip this fraction over, every time you think the series converges, it actually diverged. And every time you thought it diverged, it converged. Okay, upstairs, all the n's become n plus 1s. 4 to the n plus 1 over n plus 1 factorial. So again, everything is positive, so we can ignore the absolute values. I won't write them. I'll do my flipping thing. And here, before I'm ready to write the limit, like the calculation, the final number, I do think we need to do a little bit more algebra to clean this thing up. So let's deal with the 4s. What's left? 4 on top, 1 on the bottom, right? 1 extra 4. Okay, the factorials. Yeah, I'm hoping we're starting to get a little bit better at this. The bottom guy has an n plus 1, and then the very next term would be n, which is going to cancel completely with this here. So 1 on the top, n plus 1 on the bottom. So that means that our real fraction here we care about is 4 over n plus 1. Yeah, so this is the thing, we've seen it a couple of times, like if I had like 6 factorial over 7 factorial, n plus 1 compared to n, just the 7, right? Yeah, yeah. I would suggest that if you're not 100% comfortable with that on a homework, you just make something up. Say, okay, well, what if n is 6? All right, then it's a 7 down there, and as soon as you write it, you'll see, oh, it's just a 7 left over. It's just an n plus 1 left over. 1/7, yeah, exactly. Okay, what is this limit? 0, right? 4 over infinity. Okay. Which means that that original series is basically geometric with the common multiplier of 0. It's not that every term is half of the previous term, it's that every term is 0 times the previous term. That is how much the factorial dominates that exponential. Okay, so we just write our sentence. It looks almost the same as the sentence up above. Since L equals 0, which is decidedly less than, what's the cutoff, 1, that's your way of telling me I understand exactly what the ratio test says. We copy the series, 4 to the n over n factorial. What does it do? Converges by RT. Oh, good luck. I'd love to know what it converges to. Yeah, we just found the limit. Yeah. Hardly ever will we be able to say what the series converges to. Okay. All right. The last one is this guy right here. That looks familiar, right? We proved something about this. Go back and find it. What did we conclude, and what test did we use? This one diverged by the limit comparison test. That was the one limit comparison test thing that we did. So I just want to put out here, like it seems like the ratio test is awesome, right? It's like it's easier than some of the comparison tests we talked about. So it's tempting to just say, well, forget all that comparison nonsense. Let's just use the ratio test on everything. So I'm going to just write the highlights here to save a little bit of time. But downstairs, we would, I'm even going to do the flippy thing. So upstairs, all the n's become n plus 1s. You can write this if you want, but you really don't need to. So that's all of the n's becoming n plus 1s, divided by the original, which I will immediately flip upstairs. Okay. Equals. All I care about is the highest power. This is one of those horizontal asymptote questions. What is the highest thing on top? Give me the coefficient 2. 2 and n to the third, right? Plus lower order terms. So you imagine lots of distributing, but this is the only thing that I care about, 2n to the third. Downstairs, again, lots of distributing. So if we FOIL out this n plus 1 squared, that gives me an n squared. Then it gets doubled. Then it gets multiplied by the n over there. So it is 2n to the third. And then do you agree that everything else is going to be lower than that? There's nothing else higher than what we just did. Lower order terms are different. I don't want to imply that it's exactly the same. But if we've got this limit as n goes to infinity in the front, what is this limit? It is 1. What does the ratio test say? That's right. Ratio test needs a sound effect. The test is inconclusive. Doesn't mean the thing diverges. It means we don't know. It means you can't use the ratio test. Right? So trying to bring together, like, when do you use which test on the very next page? Here's the moral of the story for the ratio test. Try the ratio test for series that involve quotients of factorials. We did the n factorial one. Any problem you see with a factorial in it, do the ratio test. Right? Do the ratio test. Anything with an exponential, like that 4 to the n, sometimes the problem will have both factorials and exponentials, but either one, any appearance of either a factorial or exponential says try the ratio test. And powers, sometimes. Don't bother with the ratio test if all you have are powers. Polynomial on top, polynomial on the bottom. Anytime you try that, the limit will equal the, Nick? Yeah. Okay. All right. It takes experience to recognize when to use which test. I think after the 3 today, we currently have 7 different tests. It takes a lot of practice. You should have that sheet that we talked about today handy as you're working on homework and activities and stuff. But you should certainly expect to make some false starts as you wrangle with these new ideas. So there are 2 activity problems on the next page. They're going to use the techniques from today, comparison test and or ratio tests. Give them a shot.